So earlier this year, we landed a 1-ton rover on the surface of Mars, a nuclear-powered car, basically. But as we look towards the horizon, we recognize that 1-ton objects aren't going to be sufficient if we eventually want to land humans on Mars, or even more capable science missions to really understand what Mars has to offer. As we look to landing these heavier and heavier payloads, these larger vehicles, it becomes more difficult to slow them down. And so we have to find ways of taking all that energy that we put into the vehicle, to send it to Mars, and that it enters the Mars atmosphere with, and slowing it down, dissipating the energy. And the way that we've typically done that is we use what's given to us, and that is the atmosphere, and we generate drag. And in order to generate drag, you need a vehicle that has a favorable shape for producing lots of drag, and it needs to be big.
So in the last year, we've developed our first supersonic inflatable aerodynamic decelerator. We call it a NASAâs. It's our 6-meter NASAâs that inflates around a 4.7-meter entry vehicle. And we actually built our actual flight-like NASAâs out of Kevlar, and we flew it on what we call our rocket sled. It is a vehicle designed to bring it up to the pressures, the atmospheric pressures that it will experience at Mars, but we do it here on Earth on the ground on a train track. The rocket's fired, accelerates the vehicle up to 300 miles an hour. As it slows down, it fires another rocket to keep it going at about 250 miles an hour, and at that point we inflate the NASAâs right there at condition. We operate it for a few seconds and we watch it run. And it worked beautifully. We got our NASAâs out, it stayed rigid in the flow. It did all the things it was supposed to do. We got all of our measurements. We got tons of high-speed cameras watching it and instrumentation. And so we got a lot of good data on this first operation of the site. So we're very, very happy with that success.
Parachutes are just wonderful devices, and we've been using them since 1960s. In fact, they were the decelerator of choice for the Viking mission, the very first one that we landed on Mars. From an efficiency standpoint, they're very difficult to beat, and they don't weigh that much. For that 100,000 pounds of deceleration force, you have something that weighs only 200 to 300 pounds, and so the return is considerable. And so we're developing a new type and a much larger type of supersonic parachute, something that's larger than any parachute that's ever been tested supersonically before, and will generate considerably more drag than has ever been generated before.
So we're also going to need to test our parachute's strength like we just tested the NASAâs strength. And to do that, we're also going to use a rocket sled, the same facility at China Lake in Central California. But in order to do the parachute, we can't drag that one sideways like we're doing with the NASAâs. We're going to have to pull it down. And so we developed an architecture where we simply have a cord that connects the rockets to the parachute through a pulley. And the rockets will fire and pull the parachute down through the pulley as the rockets fire. And we need a lot of power. That's why we need these big rockets, because it's a giant parachute, a more than 100-foot diameter parachute that we have to pull through the thick Earth's atmosphere at 100 miles an hour to get the strength test that we need of more than 100,000 pounds load. So in the next year, we're going to be continuing our development of the parachute. We're going to have built parachutes, and we're going to have tested them on the rocket sled architecture in this coming fiscal year. We're also going to start development of our larger side. We have, in addition to the 6-meter NASAâs, we have an 8-meter side, an 8-meter supersonic inflatable aerodynamic decelerator. And that NASAâs will be developed to the point where we can put in on a rocket sled in the following fiscal year in 2014. So we expect that once we have developed this technology and we have proven it out and it's at the point where a project can adopt it, that a future Mars project, the next, for example, Mars Science Laboratory scale, the next Curiosity scale lander that goes to Mars, will almost certainly be wanting to adopt our large parachute. Mars Science Laboratory flew a 21.5-meter supersonic parachute at Mars successfully. We have developed and we're developing and will have developed for the next mission a 33.5-meter parachute, a much larger parachute, which is able to descend larger payloads at higher altitudes and will provide a lot of benefit to the next mission right off the bat. That will require relatively little accommodation modifications to something like the MSL spacecraft to take on this larger parachute. We also figured that the next mission will want to use our 6-meter NASAâs, but we think that will definitely be worth it because it will allow these higher altitudes and more precision because of the higher altitude that it can deploy the parachute at and the larger timeline it has to try and adjust for position on Mars and get to a better accuracy. And in fact, some of the entry mass could be increased as well for more propellant so that on the final stage, subsonically, it can use propellant to fly closer to the target. So there are many benefits that can be applied to the next Mars Science Laboratory scale mission with our 6-meter side and our 33.5-meter parachute.